this review. Okay. And then all right, so here we are, Unit 3. So Lesson 9 is the first one up. That was the first request, right?
Before we start, I just have 2 questions about the test.
Sure.
So first, do you have to open the camera?
When you're on the test, yes, you have to be on camera. You have to make sure your camera is working and you're on camera. And that's just the rules that are set by the school.
Okay, second question, how is like the test is like if it's like there's multiple questions or all of them are developed questions? So how is it like the structure of the test?
The structure of the test, okay, let me just actually open up the test. I do have the test made and ready here. Let me just have a look and see where we are with that, and we can talk a little bit more about that. All right, the midterm. All right, so I see here that, okay, it's a 2-hour allotment that I've set for this particular test. And let's see, in total, I have 8 questions. Okay, I have a total of 8 questions. You guys have 2 hours to write them. And some of the questions have like A, B, C parts. Some of them are just like a single question. So I think 2 hours is plenty of time to do this. You are provided with the periodic table. You are provided with a table with the standard enthalpies of formulate of the formation of various substances, like, you know, enthalpy of formation for glucose, for bromide, for diamond, for methanol, whatever. So all of those are there so that you could use those for your thermodynamic calculations. And then the periodic table is there. So, and you're provided 2 hours and it's 8 questions in total. Okay. Does that help? It's not multiple choice. It's not multiple choice. It's you have to like write your answer. And so what typically happens is in the beginning, we all join in on the Zoom meeting. And then Mr. Sohrab from the office, he emails each of you the test that I've prepared. And then he assigns you one by one to your individual breakout rooms. So once you're in the room, it's just you, and you have to have your camera on. And periodically, he or I will check in on you. We might just check in on you to see how you're doing. If you have questions, you will be able to raise your hand. I will come into the breakout room and help you answer your questions. So it's just very straightforward. So your camera will be on, but you won't be on camera with the rest of the class. Everybody is in their own private individual breakout rooms. Okay?
Okay, thank you.
Thank you so much.
Okay, yeah, no problem. So any other questions, or should we start with reviewing the thermochemistry of lesson 9? Okay, so let's start looking back on lesson 9. So lesson 9 was the first one of this unit 3. And this unit 3, altogether, all the lessons in unit 3 have to do with rates of reactions. And we started out with lesson 9, where we learned about thermochemistry and the study of the heats of transformation. And we looked at some thermodynamic terms. So Sasan, is there any particular slide that you want me to be at and to start with? Or do you want me to just go through the entire lesson?
Maybe go through like the main or the hardest parts.
Okay, well, okay. So definitely understand your thermodynamic terms, like understand that the unit of thermal energy is the joule. Understand that the chemical system that we are talking about can be open or can be closed. And what does it mean when a system is open or when it's closed? What do we mean by chemical system? What do we mean by surroundings? So the chemical system is the reactants and the products that are undergoing the energy transformation. And then the surrounding is everything that's other than the system that is capable of absorbing or releasing thermal energy. For example, it might be the beaker that the reaction is taking place in. And heat is referred to as the amount of heat energy that is transferred between substances, systems, or surroundings. And heat transfer occurs when a reaction occurs, and that takes place between the system, the substances, and the surroundings. Then the other important terms actually are, let's see, yes, exothermic and endothermic. That describes chemical reactions that where energy is released out to the surroundings are called exothermic. Exo means out. And endothermic is when a chemical system absorbs energy from the surroundings and it brings energy in. So endo means in. Excuse me for a moment.
Sorry, does being like exothermic or endothermic change the heat of the things?
Excuse me. So, pardon me, I'm just choking for a minute. So exothermic, typically the delta H has a negative sign when it's an exothermic reaction. And when it's an endothermic reaction, the delta H has a positive sign. We talked a little bit about joule and kilojoules. I apologize for coughing on you right now.
No, it's okay. You can like wait for a second so it gets like fixed.
Goodness. I took a sip of water and it got into my throat. So yeah, units of energy. Then we talked about calorimetry and how in calorimetry, it's a calorimeter is an instrument that is used in experimental techniques to measure the heat energy that changes when a reaction is taking place. And in calorimetry, we quantify a value called Q. And this is Q, the symbol Q represents the total amount of thermal energy that is absorbed or released by your chemical system. And these heat changes that take place, in order to quantify Q, you measure these heat changes by measuring the change in temperature, whether it's an increase or a decrease of the surroundings. And in a calorimeter, the surrounding is this water that typically where the reaction takes place. But just keep in mind that we don't just, temperature is not the only value that you need in order to calculate this value Q. This value Q is also dependent on the mass of the substance, its specific heat, C, and the change in temperature, which is what you're going to measure. So you need to know the mass of your substance. You need to know the specific heat capacity. Now, if you're measuring the change in heat of the water in a calorimeter, then you need the specific heat capacity of the water. If it's some other substance, then you need to know the heat capacity of that other substance, that other fluid or liquid that's surrounding your reaction and is producing that change in temperature and change in heat. So again, the value of Q has got a magnitude, so how big this number is, but it also has the sign. And when Q has a negative value, you realize that the system transfers energy to its surroundings. And so the change is exothermic. So in an exothermic reaction, a reaction that produces heat, you will notice that your Q value has to have a negative value. And if Q has a positive value, then the system is absorbing thermal energy from its surrounding, and the change is endothermic. And the water in the calorimeter decreases in temperature. And then just a few specific heat values. Any specific heat value that you might need on a test or an exam, we would give to you. I would give to you in the body of the question. I would say, given that the specific heat of water is 4.18 joules per gram centigrade, or given that the specific heat of liquid methanol is 2.92 joules per gram per centigrade. Sorry, Celsius. Why did I say centigrade? Celsius. Then we went through this example where you were asked to calculate the value Q for when 500 mils of water in an electric kettle is heated, and it's heated from this temperature to that temperature, and how much heat energy flows into the water. And the heat energy that flows into the water, you can calculate using that equation. Q is equal to mc delta T. And you just use the density of water. You're given the volume of water. The volume of water is 500 mils. We know that the density of water is 1 gram per mil. And so from that, we can calculate that the mass of water is 500 mils multiplied by the density of water, which is 1 gram per mil. And that will tell you that you have 500 grams of water. And you can use those values, then do your calculation and write your statement. We talked about the first law of thermodynamics, the law of conservation of energy, and that energy is always conserved. We can't create or destroy energy. We can only change it from one form into another. Sometimes the form that it may change into may not be usable energy. So we might view it as a loss of energy, but really this energy is not lost. It's merely converted to another form. Whether or not that form may be usable and applicable to our needs is another question. But anytime we experience a loss in energy somewhere in the universe, that energy is gained. So overall, there is no destruction of energy. It is only converted. I kind of talked about whether when you have a certain reaction, the path that you take doesn't matter. It only matters your initial and your final states. So for example, if you hook up a battery with a certain amount of energy, whether you hook this up to a filament that gets heated up and starts to get hot, or whether you hook this battery up to a fan that spins. Ultimately, you start with a fully charged battery with a certain amount of energy, and you end up with a discharged battery with a significantly lower amount of energy. In both cases, the energy lost by the battery would be the same, whether this energy is lost entirely in the form of heat when this filament gets glowing red hot, or whether this energy is lost somewhat as heat, but mostly in terms of the work that is put into making the fan spin. And of course, because of it spinning, some of it is lost as heat, but ultimately the amount of energy lost by the battery is going to be the same. So the change in energy depends only on the initial and the final states of the system, and not on how this change occurred. And this is how, if you remember in our other lessons, we were able to use formation equations and add them up and arrive at our final change in energy. What else? We talked a little bit about enthalpy H, the change in enthalpy. Then we talked about molar enthalpies and how important it is to understand that when we are talking about molar enthalpy of change, we are talking about joules per mole. So we want to know how much it is per 1 mole of that substance. And that when you're looking at these different types of delta H's for these different reactions, whether it be a solution, a combustion, or a vaporization, or a formation, a neutralization. Oh, and I also noticed when I was grading your homework that some of you, when I was asking for a delta H of formation, instead what you were giving me was a combustion reaction. So if I was asking for delta H formation of, say, methane here, you were then giving me the combustion reaction for methane. So you were taking the, instead of giving me the formation, which would be, in this case, would be like 1 carbon solid plus 2 H2 gases, right? That would be the formation of 1 mole of methane. Let me just type that out so you can see what the difference is. So the difference being that, for example, for the formation of methane, it would be carbon in the solid state. And guys, the state of these things matter. I also noticed that many people are leaving out, some of you are leaving out the state, whether it's solid, liquid, or gas. This stuff matters. Please go ahead and put it in. Sorry. And this goes to give you 1 mole of methane. So you can see right? And of course, what I mean by that is subscript and subscript. and subsequent. So when I say the formation of methane, this is what I mean by the formation of molar enthalpy for the formation of methane. You can see by looking at methane that it's made from one carbon, and you need 4 hydrogens. Those 4 hydrogens are going to come from two hydrogen gases, 2 H2 molecules. And that's the formation of methane, for example, which is very different, if you can see, from its combustion, right? Combustion is you're taking that methane, you're burning it. So for the molar combustion of methane, you got to make sure you got 1 mole of methane, and you're burning it with O2, and you're getting carbon dioxide and water. And then you make sure it's balanced out, but making sure that your methane remains 1, because this is molar, meaning you got 1 mole. But when you're talking about formation, you want to make sure that you are forming 1 mole of the methane. Just like here, this is the formation of methanol. So for the formation of methanol, you need 1 carbon. Your 1 carbon you're getting from like a graphite, a solid carbon. And then you need 4 hydrogens. So that 4 hydrogens you're getting from 2 H2 molecules. And then you need 1 oxygen. And that oxygen comes from an O2 molecule. But since you only need 1 of it, you say half of an O2 molecule. And that's the formation, right? Formation of each of these. This here is a combustion. It's a different type of reaction, okay? So that's just another example to squeeze in there. And then we said that, so the reason we can use these calorimetry experiments and figure out what is our Q, and then from that figure out enthalpy change, because this delta H is a value that's equal to Q. So that delta H can be, it's equivalent to the heat change at this constant pressure. So for example, if you're looking for, so again, these are molar enthalpies of some selected substances. And so for the molar enthalpy of vaporization of water, which is actually a physical change, the molar enthalpy for the vaporization of water. So here's water. Here in this table, you find water. And molar enthalpy of fusion, but we're not talking about fusion, we're talking about vaporization. So here's the value. So for example, you can write it, and we talked about the different ways that you can express molar enthalpies in a reaction. So that if it's an exothermic, the value would be on the reactants, on the product side of the equation, because it's being produced by the reaction. But if it's an endothermic reaction, such as the vaporization of water, when you want water to vaporize, you have to put energy in. So you have to put energy in, so it's on the reactant side. So it's H2O liquid plus 40.8 kilojoules goes to H2O gas. That's the vaporization reaction of water. So the delta H of vaporization for 1 mole of H2O is this amount. So the molar enthalpy of vaporization. Molar, we mean 1 mole. So there's not 2 or 3 or 14 H2Os, it's just 1 because it's per 1 mole. So yeah, and because it's molar, so you have to keep in mind that the delta H for 1 mole of a substance, that if you have more, if you have however many more moles, you have to multiply that by your number of moles. And the number of moles you can get by knowing your mass, and then also knowing your molar mass. And I think there's some confusion as to how you figure out the molar mass. And I think some of you need to really go and make sure you understand how you can calculate the molar mass of any given molecule, any given compound. So for example, so I mean, here in this question, you're told the molar mass of Freon is that. But if it was a molecule with many atoms in it, it was, for example, if it was this potassium chloride, well, we can figure out what is the molar mass of potassium chloride by just adding up the relative atomic masses of potassium and chloride. And because there is one potassium and one chloride, you go to the periodic table and you look up these values and you add them up, and they'll add up to 74.6. So trying to think, should I be going through this example here? Okay, so let's go through this example. For example, in this example, if you have this Freon, which is a refrigerant, and it vaporizes inside of refrigerators to help cool down the refrigerator by releasing heat. Oftentimes, if you feel the backside of your refrigerator, you'll feel that it's quite warm there. That's because this Freon is constantly cycling and also releasing heat as it's going from liquid back to gas. So this heat that's released to the outside ends up cooling the inside. This, so if you have, in this case, you're given 500 grams of Freon that is vaporized, what is the expected enthalpy change? So, so from a table, we're given that the delta H vaporization is 34.99 kilojoules per mole from the table, and the table is, I think, down somewhere. Okay, in this case, there's no table, you're just given the value. But, or maybe it was in one of the other tables. Was it here maybe? Yeah, there it is. So Freon delta H of vaporization, 34.99. So you see, you can find these values in tables. Delta H of molar enthalpy of vaporization, 34.99 kilojoules per mole. So you have to also make note of what is the unit? Is it joules per mole or kilojoules per mole? So, right, so from the table, you find this molar enthalpy of vaporization, 34.99 kilojoules per mole. You're given that the molar mass of Freon is 120.91 grams per mole, and that the mass of Freon is 500 grams. What is the delta H? First of all, we need to figure out how to solve for these relationships. So we need to know that the delta H of vaporization for 1 mole times the number of moles of this that we have in a 500 gram amount. And if you multiply those, then we get our delta H for 500 grams worth. So first, let's calculate in 500 grams, how many moles of Freon do we have? Well, the relationship is very easy, especially if you follow your units. So you know that N divided by the number of moles is equal to your mass divided by your molar mass. And if you do the division, you'll see that the grams will cancel out. the moles to the -1 in the denominator here will come up and it will become just moles. So 4.135 moles. And then you can use that 4.13 moles times 34.99 kilojoule per mole, calculate that, and 500 grams of Freon, and expected enthalpy change for its vaporization is 144.7 kilojoules altogether, not kilojoules per mole. Per mole, it's 34.99. But for 4.135 moles, it's 144.7 kilojoules. Some support questions, which I hope you guys have been trying. Let me know if you want me to go through some of those support questions. So another example was when we were going through doing a calorimetry experiment where we have some potassium chloride and it's being dissolved in some water. And what is the molar enthalpy, given that you know the final and the initial temperature? So if you notice, you'll see that the initial temperature is higher than the final temperature. The final temperature is a cooler temperature. So you know that this is going to be an endothermic reaction. So again, we write down all the stuff, all the information that we are given. So we are given the mass of potassium chloride, and it's really helpful if you just very neatly list out everything that you have. You know the mass of potassium chloride, and you know the molar mass of potassium chloride, you know the mass of water, and you know the heat capacity of water, you know the change in temperature. And write down what is required. The required is what is the final temperature of the solution. The delta H of the solution is what? And what are the equations at your disposal? Your equation at your disposal is the relationship between moles, mass, and molar mass. The other equation that's at your disposal is the Q is equal to MC delta T, and that the H of the solution would then be this Q value divided by N. Or in other words, Q is the delta H of the solution multiplied by N. So first, we want to start by calculating how many moles of KCl are there in this amount, in this mass of KCl. So we use this relationship. We figure out that it's 0.1 moles. And then we want to calculate the Q of the surrounding, the Q of the water. So we know we've got 100 grams worth of water. It has we know its heat capacity. We know the change in temperature. And the Q of the surrounding is 1.7 times 10 to the 3 joules. But we know that the Q of the system is equal to the negative value of the surrounding. So the Q of the system would be equal to positive 1.7 times 10 to the 3 joules. Then we can calculate the molar enthalpy for the system. For the system, we know this relationship and we can rearrange it and figure out our Q divided by a number of moles of potassium chloride that we have. And remember, the system is always the reaction that's taking place. And we find that the final molar enthalpy of the solution is 1.7 times 10 to the 4 joules per mole. And this is a positive value because, as you know, this reaction, this system was endothermic, right? There was a drop in the temperature. It absorbed heat from the surroundings. It did not release heat to the surroundings. It absorbed heat from the surroundings. That's why the temperature of the water dropped. So the math all makes sense. The surrounding, yes, it's negative, but then if you remember that the Q of the system is equal to the negative Q of the surroundings, then you know your Q sign will flip. And you'll end up with the right sign to match your change in temperature.
Sorry, I got one place confused. How did we get the mole for 74.6?
Yes. To calculate the molar mass of a substance, you need to look up the relative mass, the relative molar mass of each individual atom. Excuse me, each individual atom, and you need to add it up. So let me see if I can find an example here on this that we did this. This is something that I think most of you learned in earlier grades, probably in grade 11, but we can review it again here. That's not a problem, just to sort of refresh your mind. Okay, well, never mind. All we need is to open up a periodic table. So let me just open up a periodic table here. Let me search for a periodic table, or if anybody has a periodic table handy, if you could tell me what is the atomic mass of potassium, what is the atomic mass of chloride.
It says 39.0983.
Okay, so it's for potassium, the atomic mass is 35.4. For chlorine, it's 39.09. So let's see, where were we? So if you add those values up, you will get the molar mass. So you would get this value. Okay, so let's see. I'm going to put this in that molar mass of K plus Cl. And maybe a good thing to copy is this. Is equal to, what did we say? For K, we said it was 35.4 plus 39 what was it? 0.1, let's say. Actually, I think maybe this one is more like a 5. Yeah. So if we add these two up, so 39.1 plus 35.5, 74.6, correct. So just wanted to make sure I haven't made any mistakes. Grams per mole. And of course, this is all in grams per mole. If you like, you can even write it here as grams. Okay. So for example, that's how you would do the molar mass of KCl. So that's how we found the molar mass of KCl to be this 74.6 grams per mole. Now, KCl is a very simple molecule. It only has these two atoms. It has the K, it has the Cl. But say it was another molecule like glucose or whatever that has multiple C's, multiple O's, multiple H's, well, then you do just as many of those as you need. So we can get to maybe another question that might have that. Okay, so I wanted to also review this. So just remember that depending how the question is asked, for example, on one of the assignments, it was asked to write the equation, the thermochemical equation with the delta H as a part of the equation. So this is what I expect you to write. If it's an exothermic reaction, the delta H value should be on the product side. If it's an endothermic reaction, then the delta H value should be on the reactant side. Or you can, the other way to write it is just by writing the balanced equation and writing the delta H off to the side on the right side. Okay, excuse me. Then, okay, and here we went into detail about how to write these values. Okay, so here, I'm just going to take this molecule. Suppose you were trying to figure out the molar mass of this molecule here. Let's figure out how you would do that. So the formula for that, you see it has 4 carbons. So the molar mass of this C4 and H10 would be equal to the relative molar mass of 4 carbons plus 10 H's, right? And that is equal to, so 4 times for carbon, it's 12 grams per mole, plus for hydrogen, it's 1, so 10 times 1 grams per mole, for example. Okay, and then you do the math and you get, what is it, 48 plus 10, you get 58. So for this molecule is 58 grams per mole is the molar mass of this molecule. Okay, for this C4H10 gas. Does everybody feel like they understand how we calculate the molar mass of something?
Yes.
Yeah, okay. So yeah, for some common things, after a while, you start to remember. I mean, I will never remember what is the molar mass for, what is the relative mass of potassium or chloride, but I will always remember that the relative mass of hydrogen is 1, or if you want to be very accurate, it's like 1.01. For carbon, it's 12. For oxygen, it's 16, so on and so forth. You start to kind of remember some of the more common stuff. And if you don't, you always look it up on the periodic table, no problem. So what else can we cover here? Yes, potential energy diagrams. Very important to remember that you always start out with reactants and you end up at products, whether it's an exothermic reaction or an endothermic reaction. In both cases, you start, because remember, this bottom is the reaction progress. So this is the start of the reaction as it moves towards the end of the reaction. And what do you have at the start of your reaction? At the start of your reaction, you have reactants. At the end of your reactant, you have products. So always reactants are on this side, products are on this side. You never have product here, reactant here, whether it's exothermic or endothermic. Reactants first, then products. If it's exothermic, reactants start out at a higher energy. And there's a delta H minus as the products end up at a lower energy. If it's an endothermic reaction, the reactants start out at a lower energy and energy is put in because it's an endothermic reaction, and the products end up at a higher energy, at a higher potential chemical energy. Okay. And if you're asked to write, so then this is just a generic one, not saying what is the reaction, just saying some reactants converted to some products. But if you're given an actual reaction, well, the reactants go here, the products go here. The reactants go here, the products go here. Okay, so this is, for example, for the decomposition of water. You start out with water, it decomposes to H2 and half of an O2. This is for the formation of magnesium oxide, not to be confused with magnesium hydroxide, which has a hydrogen. This is magnesium oxide. So we have for the formation, well, let's see, magnesium is one magnesium and one oxygen. So one solid magnesium plus half of an O2. That's the formation of magnesium. So if they say delta H formation, that's the way you write it. If they say decomposition, well, then this is decomposing, it's breaking down to its components. If they say combustion, then please write it out for a combustion. Then write your reactants, whatever is the molecule that's becoming combusted, that's burning, and you add oxygen to it on this side, and on this side you'll end up with carbon dioxide and water. Okay, so understand the difference between these different chemical reactions that take place. All right, so that covers what we did in lesson 9 for, that was a specific request from Sasan. I'm happy to take specific questions and requests from anybody else. Sasan, Judy, Borna, anything in particular you want me to cover, I'm happy to cover right now.
I think that was my own main problem, but I'm gonna go check all the lessons again really quick to see if there's anything else.
Okay, so what I can do is I can just stay on, and if you guys want to look through, so all of your assignments are marked and with you in your shared with me folder on your Google Drive. If you look in there, you will see that all the assignments that you handed in are marked and returned to you. If you have specific questions in certain areas, we can take that up and review that. If what else? So in your Google Drive, I've shared lots with you. I've shared all the lessons that we've done are there available to you. If you guys have noticed, I am just going to share this window here with you. Okay. So in your Google Drive, you'll find that I have shared various documents with you, such as your welcome to the chemistry, to SCH4U grade 12 chemistry, such as all the different Unit 1, Unit 2, Unit 3 notes. And in the future, you will also be shared Unit 4 and 5 notes if I haven't shared with you already. Actually, I have shared it with you already. So you even have Unit 4 and 5 notes there with you. And then I have shared all the lessons that we've covered so far up to lesson 12, lesson 13, all the way to 20 will be shared with you as we go through them. And then you may have noticed that there's this Google Doc here with links to all the recordings. So every time that we make a recording, you just can go to this, click on the link, and it'll take you to that site and you can enter the passcode that's already here. So all of these lessons from 1 to 12 All the links are here shared with you. So there's been lots added and shared with you if you've gone and looked and explored all the stuff that's been shared with you. And of course, you have your Nelson Chemistry, which of course I can't open right now because I would have to download it. Your textbook is such a great resource to have. There's just so much information in there. Oftentimes, a lot of the pictures and diagrams and graphs and charts and tables I get from the Nelson Chemistry textbook. Okay. So I can let you guys skim through your notes quickly. I can just stay here and you can ask me questions. Or if you want, we can just keep on going with the review and move on to reviewing a little bit more of lesson 10, lesson 11, and so on and so forth. So right, we did Hess's law, whether or not something happens in one step or more than one step. You can combine the equations algebraically according to that. So most of you did really well on these types of questions. Yeah, you did very good. You were very good at figuring out, okay, so based on the equations that are given, which one do I have to reverse? Which one do I have to reverse and multiply by some number? And what are the terms that cancel out? And that's how I will arrive at the final enthalpy for that reaction. So I didn't see any problems anybody doing these. I think sometimes I think I saw just mistakes that weren't really from lack of understanding, just being careless and not careful with your numbers. But yeah, I didn't see any problem with these types of questions. You guys all got it. You understood how you can figure out this type of question. What else did we do? Standard enthalpies of formation. So you can use these standard enthalpies of formation to also figure out the enthalpies of certain reactions. So we can look at some examples, and keeping in mind that the enthalpy change for a certain target equation would be the enthalpy formation for all of the products minus the enthalpy of formation for all of the reactants, okay? And these standard enthalpies of formation are found in this Appendix A at the end of the lesson I had here. So you can see these are standard enthalpies of formation, delta HF naught, or standard enthalpies of formation. And they are here for the various compounds that you can look up and it's relevant to you. If anything like this needs to be done on the exam, you will be provided such a table for you to look up your information in. So, right, so in this question, for example, right here, I just wanted to review these relationships again, but I think most of you understood this relationship from what I could tell from marking your homework assignments. You understood all of this. Some of you forgot a little bit about this rule, that this is how you can find the enthalpy change for a target equation using these standard enthalpies of formation. And I think the important things to understand here is that for elemental products in their, what's the word I'm looking for? For the delta HF of an element in its standard state is 0, for example. And I think I saw that that was also clear to you, so that the delta H formation for things like H2, O2, N2, Cl2, anything in its solid state, in its standard solid state, for all of those things, it would be 0. All right. So here, for example, again, we're using, this is our target reaction, and we're asked to, what is the molar enthalpy of combustion of methane fuel? Okay, so methane looks something like this. And how do we combust it? Well, we combust it with oxygen, and it yields carbon dioxide and water. That is a standard combustion reaction. So the combustion reaction has got reactants, has got products, and it has reactants. So we can use this knowledge that the enthalpy of the reaction is equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. So first we write out our big square bracket, understanding from here to here. This is where all our products are going to go. So what do we have? We have 1 mole of CO2, and we look up in that table in Appendix A, and we find the value is minus 393.5 kilojoules per mole. And we add that to, what do we have? We have 2 H2Os in the liquid state. In the liquid state, 2 moles times 285.8 kilojoules per mole. And we sum them all up. We add these up and we get this value, minus 965.1 kilojoules. And then we want to subtract that from our reactants, the sum of the delta H formations of our reactants. So minus, then we figure out what is the delta H formation of all of our reactants. And what do we have in the reactants? We have 1 methane and 2 O2s. So 1 mole for the methane times the delta H formation of methane is minus 74.4. We find that in the table, plus 2 moles for the 2 moles of the O2. But for O2, it's 0 because it's the standard state of that element. So it's 0. So that ends up just reducing to minus 74.4 kilojoules. We do our subtraction of our products, the sum of the delta H formation of our products minus the sum of delta H formation of our reactants, and we get our answer. And because it's per mole, that's what we're asked to find out, the enthalpy formation per mole. So the molar enthalpy of combustion of methane is that, okay? Anytime you see the word molar, that means your unit has to have a per mole in it. Okay, here was another question. Again, another combustion question, this time the combustion of octane. So you know that this is the formula for octane from our previous units. You figure out that octane is a hydrocarbon, 8 carbons, and all single bonded together all around it. It's filled with hydrogens all around. So altogether, there's 18 hydrogens on that, no problem. So this is our octane. And then it burns with O2, it yields CO2 and H2O. You make sure you balance your equation and calculate and you're asked what mass of this octane is completely burned to cause the heating of 20 grams of aqueous ethylene glycol automobile coolant from 10 degrees to 90 degrees. See, in this case, it's not water that we're measuring the change in temperature for. In this case, it's in an engine, and it's the engine coolant, the automobile coolant, that is absorbing the heat and is changing temperature as a result of the combustion of methane, as a result of this reaction. So, and we are given that the specific heat capacity of this ethylene glycol, this engine coolant, is this value. And we are told that assume that water is produced as a gas. So we make sure when we write our equation, we put a G in here and not an L, so that then we can find the appropriate value for it from our table. So these are all details that you need to underline when you're reading the question. You need to underline that, make sure you have your gas in there, make sure you have, the question is what mass. So ultimately you want to know what amount of this octane was burned to produce that amount of heat. So first we have to calculate the molar enthalpy of combustion of octane. And we figure out that for this reaction, again, it's delta H formation of all the products minus delta H formation of all reactants. And the products are what? Are CO2. We've got 8 of them, 8 moles times delta H formation of CO2 plus H2O. H2O, we got 9 of them, and we make sure we get the value for H2O in the gas state, not H2O in the liquid state. They're different numbers. And we sum those up, and then we subtract from, we have 1 mole of this octane. So for 1 mole of octane, the table tells us that it's 250.1 kilojoules per mole. And we add it to O2. Our O2 is 0. So 25/2 moles multiplied by 0 kilojoules per mole. This whole term becomes 0. And we finally do our math, and we end up with delta H is equal to the molar enthalpy of combustion of this octane is that, okay? Now, we have to assume that this heat that's produced by this reaction, this amount of heat that's produced by that combustion reaction, is absorbed by this ethylene glycol, this engine coolant. That's how it dissipates heat from the car. So it's absorbed by this engine coolant. So this delta H of the octane is equal to Q for the coolant. And then we need to figure out, okay, so what is the molar mass of octane? All right. So we need to figure out that we've got molar mass of octane is equal to, octane has got 8 carbons, 18 hydrogens. So 8 times the relative molar mass of carbon. And remember, for carbon, it's 12.01. This is a value that you'll find on the periodic table. And for 18 and 18 of the hydrogen, and hydrogen is 1.01 grams per mole. So you add these up, and we find out that the molar mass of octane is this value. All right. And then we can use that to figure out what mass of octane we have. Then we solve for first that's how we figured out what's the molar mass of octane that we have. Now we want to solve using this relationship for how many moles of octane we have. So we know that this value that we calculated, this delta H of octane would be equal to the Q for this ethylene glycol, the Q for ethylene glycol. So this is also the term that equals Q. So Q is related to this delta H of combustion through this number of moles of octane that are burned. So is equal to our 20 grams of ethylene glycol multiplied by the heat capacity of this ethylene glycol. So all of these values are the Q. We put them in, And then we divide it by the delta H for the combustion that we figured out here. And because this is what we figured out for 1 mole. So if you can see, this is 1 mole. So we can easily write per mole and figure out that how many moles of octane have produced this Q value based on the delta H of that combustion reaction. And we figure out that it's 0.0011 moles of octane. And then we can use the relationship of moles and molar mass to figure out how much is the mass of octane. And we can figure out that 0.126 grams of octane is burned to heat 20 grams of the coolant by 80 degrees. Okay. Any questions that I could answer for you? Let me know. How was the chemical kinetics lesson for everybody? That was pretty clear, right? Okay, so everybody understands that rate of the equation is equal to some rate constant K multiplied by the concentration of the reactants raised to some exponent. And this exponent is called the order of the reaction with respect to that reactant. And so for example, if we have a rate equation, some rate equation that looks like this for a reaction that looks like this, this is very generic. And say, for example, now these numbers don't necessarily relate to these exponents, right? So say we had this, the way we talk about this, we say that the rate is proportional to obviously concentration of X raised to the power of 1. It's also proportional to Y raised to the power of 2. And it's also proportional to Z raised to the power of 0. And that's why we are able to solve these types of questions where we can use a method of these, what's called the initial rates method, to determine the rate law for some reaction, for example. Here we have some reaction where acetone and bromine are reacted together, and you're given that the Rates law is of this form. And then you were given this experimental data. And a good way of determining the rate for various reactions is by pairwise changing the concentration of one of the reactants while keeping the concentration of the other reactant constant. For example, in the two experiments, experiment 1 and 2, if you notice, they kept the concentration of acetone constant, but they changed the concentration of the bromine. They doubled the concentration of bromine and then measured the rate. And when they measured the rate, we saw that keeping the concentration of acetone constant and doubling your concentration of bromine, that does nothing much to the initial rate. It seems to have no reaction, no effect on the reaction rate. So by examining the fact that there is no effect on this reaction rate, we say that the overall order of the reaction with respect to this, this bromine with this bromine is 0. And that it seems to have, not affect the rate of the reaction. You can double it and your reaction rate is still the same. So now let's look at two other experiments. Which would be a good choice to compare? Again, we want to compare the next set of experiments that we compare. We want them to be experiments where, again, a product is kept constant while the other one is changed. So we already looked at the one where bromine is changed and acetone is kept constant. Let's look at one where bromine is kept the same and acetone has changed. So that looks like that would fit the bill. Experiment 1 and experiment 2. So here you can see if we compare these two, experiment 1 and experiment 3, the 0.1 and 0.1, the concentration of bromine is kept constant between these two experiments, but the concentration of the acetone has been doubled from 0.1 to 0.2, it's doubled. Then we look to see what's the effect on the reaction rate when this concentration is doubled. And we see that when this concentration is doubled, the effect is that this concentration is also doubled. So therefore, the reaction must be first order with respect to acetone. So looking at those rates and comparing them, we can figure out what are these exponents m and n. And we figured out that with bromine, it would be 0. With acetone, the order would be 1, because when you double it, the rate doubles. And keep in mind that in practice, we'll likely never see a reaction with an overall order of reaction that's any higher than 3. And if you calculate an order of reaction higher than 3, please go ahead and double check your math. You might have made a mistake. All right, so this is just another example of exactly the type of question that I just talked about. So you're given a certain reaction, you're given a certain data, you're told how it changes. You go ahead and compare the data pairwise, and you make sure you compare. For example, here you see I'm going to compare 2 and 3, because in 2 and 3, this is kept constant while that one has doubled. And I'm going to see what does doubling have on the how does it affect my initial rate of reaction. Likewise, I can compare these two, experiment 1 and 2, where this is kept constant and this has changed. So from here to here, it's doubled, this bromate. So we go and look to see what's the effect on the initial rate of reaction. And that will tell us what the value for M and N are respectively. We can see that when things, if you end up doubling something and your reaction rate doesn't change, then your order of reaction is 0 with respect to that. If you end up doubling something and your order of reaction also doubles, then that means your order of reaction is 1 with respect to that. If you end up doubling something and your order of reaction quadruples, then that means your order of, if your reaction rate quadruples, your order of reaction is 2. If you triple something and you're one of the reactants and your reaction rate increases 9-fold, then again, you know that your order of reaction is 2 with respect to that reactant. And so on and so forth. You can see the math relationship. Okay. And K being this rate constant can have different units depending on the total reaction order. And if you recall, total reaction order is just the sum of that m exponent plus n. So if for a reaction total order reaction of 0, the units are generally this. For a total reaction order of 1, the units are generally this. 2, it's this. 3, it's this. And you can actually figure this out by using this type of scheme to figure out what would the rate be, because rate is always expressed as moles per liter seconds. That's always how rate is expressed, because it's a change of concentration over a certain time. And concentration is always moles per liter, right? So that leaves behind us trying to figure out what are the units for K in this case. So in this case, the units for first order reaction altogether is 1/s, as we figure out, as we cross out. If we have overall order of, this was if it's to the exponent 1. If say it's an overall reaction of 2, then you got to put an exponent of 2 around this term. If it's 3, you've got to put an exponent of 3 around this term, and then do the math and see what's the K. All right. A little half-life. Half-life, we understand what it means. So basically, half-life is a time it takes for a substance to go from a starting concentration to a concentration that is half of what it started with. That is the definition of half-life. And for your typical first order reaction, it can be calculated using this relationship. And what else? Collision theory. We talked about these energy diagrams. We talked about the idea of activation energy. The activation energy is the amount of energy that needs to be put in for the reactants to be raised to an energy level associated with the active complex, or the activated complex, or the transition state up here. And that's how much energy is needed in order for the reaction to occur. That's the amount of energy that needs to be overcome. That's the amount of energy that needs to be supplied in order to break those bonds in the reactants and to form the bonds in the products. And again, it's the same situation, whether it's an endothermic reaction or an exothermic reaction. The activation energy is always the energy going from the reactants to the top of this activation barrier, to the top of this transition state where this activated complex would be. And this, in a slow reaction, the activation energy would be greater. There would be more energy that needs to be overcome. Whereas in a fast reaction, you can imagine this activation energy, this hill would not be quite so high. It would be a shorter hill. And then we talked about the factors affecting the rate of chemical reactions. And then we talked about elementary reactions. And that when you had a complex reaction mechanism, something like this, we can be certain that this is not going to happen in one shot, because the probability, the likelihood of this many molecules altogether in this example, 7 molecules colliding together at once with enough energy at the perfect orientation, this is very unlikely. chances are this reaction is taking place through steps. And these elementary reaction steps typically only involve 1 or 2 molecular collisions. Very rare for it to be 3. So don't really consider these much. It's mostly these types of reaction, either unimolecular or bimolecular. And for elementary reactions only, not for reactions with the overall balanced equation, not for these types of reaction, but for elementary reactions, such as these, where a single product is, a reactant is going to a product, or a product A is hitting another, reactant A is hitting another reactant A and becoming products, or reactant A is hitting reactant B and becoming products. These are elementary steps. For elementary steps only, you can determine the coefficient, the exponent for the rate equation based on the coefficient of for that reactant in the equation. Okay, so you can see here for elementary reactions only, you can determine that the rate law for this kind of a reaction would be that, and you can confidently put 1 over here. For this kind of a thing, if it's an elementary reaction, you can confidently put down this. Or if it's this sort of a situation, you can confidently write down the rate equation as this. Or if it's this, again, that. This situation is just too rare to really talk about. We're not going to consider this very much. It's so rare. So for example, we can go through this example, or if you want, maybe through this next example. So here, let's say we have got this overall reaction mechanism. And then we've got to think about, okay, so does this happen? It cannot happen in one shot, because look, we need 4 molecules of hydrogen bromide to collide with 1 molecule of oxygen. All 5 of these need to collide at the exact same time with the exact right amount of energy to overcome that activation barrier. They need to be oriented in the perfect orientation. And this needs to happen simultaneously for 5 things. This is highly, highly unlikely. So chances are this is going to happen through a series of simpler elementary steps such as these. And here it's been suggested, what are these? But you can certainly think of some yourself in a much simpler kind of a reaction. For example, this one might involve only these 2 steps. You can imagine if you have this, okay, this is not going to happen because it involves 3 reactant molecules, very rare. Again, according to atomic collision theory, yeah, this is not something that's going to happen. So if we think about this logically, we'll think about this as what's happening. Okay, probably we've got 2 of these colliding together to give what, something maybe like that. And then maybe something like that will collide with that oxygen. And then we can have our 2 nitrogen dioxides at the end. So we can think of possibly these 2 steps happening. And we can notice that if we add then these 2 reactions together, the overall reaction is exactly what our target reaction was. And that the dinitrogen dioxides cancel each other out, and we'll end up with our target reactions. Now, this dinitrogen dioxide is called a reaction intermediate, and it's typically very short-lived. It's not something that can be typically isolated or visualized or purified in the scheme of the reaction. It's almost as quickly made as it's quickly consumed by the next step reaction. So although it's not possible to predict what the reaction mechanism would be, but we can, if we are given some of these steps of a reaction mechanism, we should be able to figure out how to add them together in individual steps to end up with the overall reaction mechanism. And also we are able to make judgments on which ones would be the fast steps or the slow steps. So here on this slide, I went through what are the steps you need to consider and keep in mind as you're kind of proposing some reaction mechanism and evaluating it. First of all, what you need to keep in mind is that, so, okay, these equations, these elementary steps need to be able to combine to give your overall target reaction. Okay, so make sure that that is there. So number two is that make sure that these elementary steps that we're proposing are reasonable and they don't involve more than 2 reactant molecules. Any more than that, and you're kind of getting unreasonable, unlikely that it's going to happen. Then you have to also, the mechanism must support whatever is the experimentally determined rate law. So for example, in this example that we looked at earlier in our lessons this week, if we are given this, this reaction, which is the decomposition of dinitrogen pentoxide. So it's decomposing, it's breaking down into O2 and dinitrogen tetroxide. So, and we are given, suppose that the actual rate law is this. What is the rate determining step? Well, because the coefficient on the reactant must be the same as the exponent in the rate equation. So, so we have to break down our steps and think about, okay, which one of these as an elementary step would give this kind of a rate equation. Because remember, the rate is always determined by the slow step. So the reaction that gives this kind of rate equation will be our slow step and it will be our rate determining step. In this case, it's this reaction, this step, this elementary reaction that gives this sort of a rate equation. Because look, we have N2O5 and to the power of 1. It cannot be this because the rate equation for this will look like that. And that cannot be because, first of all, this does not look like that. No match. And also because the oxygen is an intermediate, reactant. And you don't want a reaction intermediate like this to be a part of our rate equation. So there's these clues that tell you, okay, this is not our slow step. This is not our rate determining step. This is our slow step. This is our rate determining step. And this one must be our fast step. Okay. And I didn't really go into these. I think they're more detailed for students who are more interested in learning more about this in a bit more detail. My previous term that I taught this course, there was a couple of students who were interested in learning about it at this level of depth of understanding, and it's very useful. It's you definitely understand how to evaluate these. If your first step was your slow step, or if your first step was your fast step. There's different ways of evaluating it and going on. Okay. All right. Just wanted to bring this to your attention that when I ask for a structural formula from you guys, I'm not asking for the condensed formula and not asking you for the molecular formula. When I say structural formula, please give me the structure. Don't give me a line diagram. Don't give me a condensed formula or a molecular formula. These, as you can see, are very different than this. Okay, so please write this out and please take the time to put in all the bonds and every single atom that is involved in that molecule. And of course, in Lewis diagrams, please make sure to put in every single dot for the electrons in the valence shell. All right, guys, it is 7:30. We still have half an hour. I'm happy to entertain questions relating either to this unit 3. I also have lined up for you unit 1 and unit 2 for your review. Anything from these lessons that you would like me to go through, please let me know. So yeah, please let me know and I will be happy to provide you the right discussion. So please know how to do, obviously I expect at this point everybody to know how atomic number, how mass number, how the number of electrons, protons, and neutrons are obtained by just looking at values on the periodic table. Everyone should know this. Everyone should be able to fill out this type of a chart to figure out, given any of these informations, what else needs to be filled out. You guys should all be able to do that at this stage. You guys should be very familiar with writing out electron equations for each one of your, for whatever element or ion. Okay. You should be able to provide these electron configurations just by being able to look at a periodic table. You should be able to write out the full electron equation, electron configuration for each one of these atoms or ions. Sometimes you have to pay attention. The question is asking for an ion, for example. If you think back to key question number 2 from the very beginning of the course, you were asked the energy level diagrams for beryllium, magnesium, and calcium ions. So for all 3 of these, you were asked for the ion. So energy level diagrams for all 3 of these in the ionic form, in their ionic form. And then same with this question, you were asked how the sodium ion, not just the sodium, just the atom, but the ion. So here, I mean the Na+1 sodium ion and the neon atom. How are they, write the electron configuration, describe and explain similarities and difference, because they have the same electron configuration. So at this point, yeah, you should feel very able to do that. You should have no trouble with Lewis structures. So when you're drawing a Lewis structure, you write the atomic symbol of the element in the middle, where it represents the nucleus of the atom, and it's considered to have like 4 sides, and place the number of valence electrons that it has, 1 per side, and then begin pairing it up if necessary until it's all filled up, or whether you have 1 lone pair left or not. That's yeah. So for example, yeah, some of the Lewis structures and the valence shells. So for carbon, it looks something like this. For oxygen, nitrogen, phosphorus, aluminum, magnesium, so on and so forth. Okay. You should understand electronegativity and how you can use electronegativity to determine the polarity of a bond, whether it is non-polar covalent or polar covalent or ionic, based on the value of the difference in electronegativity of the atoms that are involved in that bond. You should be able to indicate what type of bond it is, whether it's ionic, polar covalent, or covalent or non-polar covalent. For example, you should be able to do ionic, to be able to draw Lewis structures for ions, for elements that are involved in ionic bonding, for example, magnesium and nitrogen, for example, sodium and chloride, calcium and chloride, so on and so forth. I think we did some of these examples here. For polyatomic, you guys should be able to do that. You guys should have a clear understanding of the VSEPR theory and how you can use VSEPR theory and what type of geometry various molecules adopt, at least some of the most common ones, such as H2O and CO2. And based on that, you should be able to tell, given a molecule, whether that molecule is polar or not. That was some of the exercises you had, where you asked to determine if a molecule is polar or not. So you first have to look at what is the polarity of the bond, whether there's polarity in the bond. For example, here, if you look at the electronegativity, if you look at this molecule of carbon tetrachloride, it's one carbon with 4 chlorines on. And if you look at the electronegativity between carbon and chlorine, the electronegativity is 0.5. So these bonds are considered to be polar covalent, and that's why we put this delta value of negative and positive here, because these chloride ions tend to have a bit more pull on the electrons from the carbon. So it's giving the carbon a partial positive charge, and chloride is having a partial negative charge. So this makes the chlorine ends, or the chlorine dipoles, slightly negative, and the carbon slightly positive. But overall, because of the symmetry in this molecule, because it is falling into this kind of a geometry, where is it? I just want to remind you that it's falling into this kind of a tetrahedral geometry, and because it's symmetrical, that overall the molecule is not polar, even though the bonds are polar. Okay. And of course, you have to consider if there's any lone pairs, non-bonding pairs of electrons over there, then definitely that is gonna affect the polarity of the molecule overall and the shape of the molecule, because these electrons tend to have a bit more stronger repulsion than these electrons that are in the bond. So a molecule like ammonia, because of the presence of this lone pair of electrons, will have this pyramidal shape, because the lone pair of electrons that you can imagine are up here tend to repel these electrons that are involved in the bonds a bit more. Then you get this pyramidal shape. Okay, you should be clear on intermolecular forces. That bonds between molecules. So those being things like London dispersion forces, dipole-dipole forces, and then finally hydrogen bonding. Okay. Please understand capillary action and adhesive forces versus cohesive forces. All right, so that was Unit 1. Quick review of Unit 2. What did we learn in Unit 2? Yes, in Unit 2, we covered hydrocarbons. We covered naming of hydrocarbons, of saturated hydrocarbons, and prefixes of meth, eth, prop, bute, pent, hex, hept, oct, non, and dec. And for a saturated hydrocarbon, where every single carbon and hydrogen bond is only a single bond with nothing else but hydrogens and carbons, it would be an ane. It's an alkane. This class of molecules are referred to as alkanes. They have the ending ane. So methane, ethane, propane, butane, and so on. If these groups are a branch off of another part of the molecule, then we call them that these are alkyl groups, and they have the same kind of prefix except they end in -il. So methyl, ethyl, propyl, butyl, etc., so on and so forth. And please review IUPAC rules for naming alkanes. I will tell you right now, on the midterm, I will be asking you to either give the name for a certain compound whose structure I will write, or I will give you the name and I say, draw the structure of this compound. So make sure you understand how to do these. Okay. Yes, make sure you understand functional groups. Alcohols will be OHs. And you always want to number your alcohol compound in a way that the lowest number will fall on the carbon that has the OH. So for example, in this type of molecule, we want to start numbering from this end, because then the carbon with the OH will get a 2. Whereas if we start numbering from this end, then the carbon with the OH will end up getting a 5. So this is a more desirable way to number it, so that the carbon with the OH group will have the lowest number possible. And then this would be called 2-hexanol. Cyclic alcohols, aromatic alcohols. We talked about the benzene group. Another way to name this is it's called a phenol if it's a side branch off of another off of the rest of the molecule. It's a phenol. Make sure you understand that this benzene ring, this phenol, is different than just a cyclic hydrocarbon. The cyclic hydrocarbon, there's only single bonds all throughout. You don't see any double bonds. But in the phenol, in the benzene ring, every other bond is a double bond. That's important to note. Know what are your ethers and aldehydes and ketones. Your carboxylic acids and esters and amines and amides. Okay, also be aware of the type of organic reactions. Remember, we had addition reactions, and the addition reactions we covered fell under 4 types: hydrogenation, halogenation, hydrohalogenation and hydration. These were the addition reactions that we studied. Very important to remember the Markovnikov rule, where the rich gets richer. The hydrogen always goes to the carbon in the double bond that already has the most hydrogens. It's already rich with hydrogens and it's about to get richer. Now it started out with 2. This hydrogen is going to choose to go here and now it'll have 3. The rich got richer. Okay, we talked a little bit about condensation reactions and the formation of polymers such as glycogen. We talked about condensation reactions and the formation of not only collagen, but also in the formation of proteins. The formation of this peptide bond is an example of a condensation reaction where water is removed out. We talked about combustion reactions. And I think we've looked at enough examples involving combustion reactions that everybody should be very clear that when you have a combustion reaction, your reactant molecule that is being burned, that is going through combustion, is reacting with O2. Remember, you always need oxygen for there to be a fire. So in a combustion reaction, it's reacting with O2, it's reacting with oxygen. And at the end, you get nothing left but carbon dioxide gas and water vapor. Sometimes in a combustion equation, they choose to write this in the liquid state. In that case, if you're asked to do thermodynamic calculations and delta H formation values are required, remember there's different values for whether it's a gas or a liquid. And make sure you get the right number from the table. Yeah, oxidation reduction reactions, good to know. Polymers, yes, we talked about these in great detail. This is where a certain amount of overlap comes. Actually, a lot of these lectures, there's quite a bit of overlap between this grade 12 chemistry and the grade 12 biology. I don't know, some of you are also taking biology, grade 12 biology, or might be taking it in the future. A lot of grade 12 biology covers these grade 12 chemistry concepts that we have talked about here. Okay. All right, that brings us to the last few minutes of our class. Anybody have anything specific?
No question. Thank you so much.
Okay, thank you so much. Go ahead and please set enough room, and I went ahead and wrote the correct answer in for you. Sometimes there wasn't enough room and I just put in an X, and I just want you to either go ahead and look it up and try and find out why you went wrong and why you made a mistake. But if it really baffles you, if it really confuses you, and no matter how hard you think about it and how hard you look it up or look at whatever comment or note I made, you can't figure out why I marked that question wrong for you, please feel free to send me an email and I will respond, and I will help explain to you what would be the correct way to answer that type of question. Okay. All right, I wish everybody good luck studying. I hope you all study well. Make sure you stay adequately hydrated, drink your water so that you don't end up dehydrated and with a headache. That's always really important. And yeah, I'll see you guys Friday at our midterm at 6:30 in the evening, okay? All right. Have a good night, everybody.
Thank you. Have a great night.
Thank you. You too.
Thank you. Bye.
Goodbye.
Bye.